Hello and welcome to the sequence of videos on hypothesis testing. In this video, we're going to talk about the two-sample t-test. Let's get started. So when do we perform a two-sample t-test with independent samples? A two-sample t-test is supposed to be performed when you're trying to compare the means of the two independent groups to determine if there is a significant difference between them. What do we mean by independent groups? Independent groups mean there is nothing that's overlapping between them. I'll give you more examples to clarify it further. Coming to the assumptions of two-sample t-test. So some of these assumptions continue to be the way they were in the previous test. For example, the sample should be selected randomly. There is supposed to be an independence between the observations within a sample, and even the two samples should be independent. The normality of the parent population. So the samples are assumed to have come from populations which are normally distributed. And an additional assumption that you see here, which is known as homogeneity of variances. Please note this assumption can itself be checked through certain other hypothesis tests. But what is this assumption about? This is an assumption about the variances of the parent population from which the samples have been collected. They are assumed to have equal variances. But this may not always be satisfied. There are ways to conduct the test even without this assumption being in place, and we'll talk about that too. So every test involves a test statistic. What is the test statistic for a two-sample t-test? This is the general statistic. It talks about the difference between the two sample means. So let's say you have two samples like 1 and 2, and x1 bar and x2 bar here represent the average of these samples. And we are dividing it by the standard error of the difference between the means. There are two different approaches. First approach assumes that the variances of the populations from where these samples have come were equal. The calculation of standard error in case of equal variances involves calculating a pooled standard deviation, which is calculated like this. So N1 is the sample size of first sample, N2 is the sample size of the second sample, S1 is the standard deviation of the first sample, and S2 is the standard deviation of the second sample. If this seems like too much of calculation, trust me, today we don't have to actually do this manually. There are tools which do it all under the hood for us. So I'll show you the easiest way to go about this. Once you calculate the pooled standard deviation, in order to calculate the standard error, which is mentioned here, you have to put the pooled standard deviation and further add the square root of 1 divided by n1 plus 1 divided by n2. So this is calculation. And once you put these values here, you can calculate the t-statistic. The degrees of freedom, this concept was explained in the previous video on one sample t-test. Because you have two samples now, it will be n1 plus n2 minus 2. If we do not assume that the variances are equal, then the calculations vary a little bit. So the general test statistic remains the same, but the calculation of standard error is different. Now, we don't have to worry too much about the math behind it because we are looking at it more from an applied side of it, right? But like I said, we have tools these days that take care of all this under the hood, so we don't have to manually do all of this calculation. Now, let's move on to a problem and understand this a little better. So the problem states there are two internet service providers, A and B, who operate in the region where you live. You want to check if they provide comparable speed. You and some of your neighbors who have been using internet services have collected these speed test results in two separate samples. Sample 1 belongs to provider A, and sample 2 belongs to provider B. So you see why these samples are called independent? Because A has nothing to do with B. A is a separate provider, a separate company. And when you check their internet services, those are not influenced by what provider B is doing in that region, right? So they are independent. And these are being measured in megabits per second. That's the typical unit for internet speed. It is mentioned that the samples have been provided in a file called internet speed. Conduct a hypothesis test at 5% level of significance to check if there is a significant difference in the average speed offered by the two providers. So what are we doing? We are comparing the average speed of provider A with the average speed of provider B. We are comparing two means, and the samples are independent. So now going by the step-by-step approach, do we know the level of significance? That's stated in the problem as 5%, which means alpha is 0.05 or 5%. What is the hypothesis? The null hypothesis is that there is no difference between the two providers. We'll check it for equality. Notice in the problem statement, it doesn't talk about whether provider A has a better speed compared to B or B has better speed compared to A. It simply says, are they different? So we are checking for equality in the null hypothesis and checking for them being unequal in case of the alternate hypothesis. The claim is not directional here, which means it is a two-tailed test. At this stage, I would like to take you to the raw data and would want to just understand some descriptive statistics around it. We'll be back with a visual explanation of this hypothesis, and we will also be solving this properly using tools. Okay, so we are here looking at the file called internet speed, and we can see the data here. So we seem to have two samples, sample 1 and sample 2. Sample 1 has 15 observations and sample 2 has 20 observations. Please note, it is not mandatory for the independent two-sample t-test to have equal samples. That's why you could see N1 and N2 representing the sample sizes. Now that we know these are the two samples, we can go about calculating the descriptive statistics around these samples. For example, we can easily compute the mean and standard deviation. So let me explain this problem to you visually now. So this is how the samples look like. So let's understand the descriptive statistics of these two samples. As we saw the raw data, we could have easily computed the mean and standard deviation. So the mean of sample 1 is 22.06 and the mean of sample 2 is 25.77. The standard deviation of sample 1 is 1.68. And for sample 2, it's 1.50. Sample size for the first sample is 15. For the second sample, it is 20. So let's see how we go about solving this in Excel. We will not necessarily do the calculations manually, but we'll be using the functions which are available in Excel to solve this problem. All right, so once again, we are back to Microsoft Excel. And in Excel, under the Data tab, it could vary a little bit depending on which version of Excel you're using, but under the Data tab, you have something called as Data Analysis. If you don't see it by default, just search it, you'll be able to get it using Excel add-ins. So I'm clicking on this option called Data Analysis, and if I scroll down, you can see we have a couple of tests mentioned here. The one that we are interested in would be t-test. Right now, we'll first do it with equal variances, but you can see a similar test for unequal variances is also available here. So let's take the equal variances option and hit OK. Now it's asking me to select the sample 1. So I'll be able to select sample 1 here. And then it's asking me to select the sample 2. So I choose the second sample. Do we have any hypothesized mean difference in mind? So we are checking for their equality. We may put this as 0. See, you could also check for a predefined difference. Let's say you're saying that the speed differs by more than 4 megabits per second. But that's not the case in our scenario. We are talking about whether there is a difference or not. Do we have labels in these columns that we have selected? The answer is yes. We have a header here which says sample 1 and sample 2 for the second sample. And let's go with the alpha of 0.05. It will give us the solutions in a separate worksheet. That's the option we are choosing. So as you can see, some output has come. Let's try to zoom in here and understand this a little bit. See, it is giving us the descriptive statistics that we saw on the slides. So the mean of sample 1, sample 2, the variance, the number of observations, the pooled variance. Remember that formula that I showed you? This one, this is the calculation that it's reporting. And then hypothesized mean difference, of course, we had put it as 0. Degrees of freedom, 33. Why? Because you have 15 plus 20, 35 samples. The degrees of freedom in this case are N1 plus N2 minus 2, as shown on the slide here. There is a t statistic that has been calculated. How is this being calculated? It is being calculated by putting this standard error here. And then it is calculating two different p-values. First is assuming that it's a one-tailed test. Now, in our case, it was not a one-tailed test because we didn't have a greater than or less than condition in the alternative hypothesis. We just had a not equal to condition. So we'll go with this p-value, which is essentially pointing towards two-tailed tests. And we'll also be referring to this critical value, not the one-tailed critical value. The critical value in our case is 2.03. So another advantage of using a built-in function here is that when you get this p-value and it is declared that it is a two-tailed p-value, you don't have to do any adjustments here. You will simply compare it with alpha. Now, this value, if you see, is written as 7.58. Then this e minus 0.8, this basically means 10 to the power minus 8, which means you're dividing by something which is like 100 million or 10 to the power 8. So of course, you can clearly see this is definitely going to be a lot less than 0.05. Now, what is the decision rule? If the p-value is less than alpha, we go about rejecting the null hypothesis. Let's see this visually. So here is our scenario. What you see here, this plot, it basically is a plot indicating the difference between the two means. And we put it on the standard t distribution, the critical value that we computed for two tails, 2.03, you can see here. And the test statistic is negative 6.87, right? So you can see this shaded region is representing the rejection region. And of course, to the left of the lower critical value here, you can see the test statistic is very well within the rejection region. This area is not even visible because it's a very, very small area, but you can imagine the test statistic is falling in the rejection region. So this is what your conclusion would be looking at the critical value. And of course, the area to the left of it, which is what we will call the p-value, is definitely going to be less than the level of significance. Notice that a t distribution would always be defined with respect to the degrees of freedom. And you can see this is not just any t distribution, this is a t distribution with 33 degrees of freedom. So this is the visual explanation. Now, what if this was a test with unequal variances? We again don't have to worry too much about the maths behind it, but under the data analysis option, you can see that's a second choice, right? This will have a pretty similar interface where you can choose the two samples and it'll do all the calculations in line with this slide because we are assuming the variances to be unequal. Let me perform these tests for you now in Python. All right, so we are here and we of course have to call a couple of libraries. So for example, because we are going to read an Excel file, we need the library called pandas, and we will also be needing the library which holds all these tests. So we have this available in the SciPy library stats module. The test is called t-test independent. We are reading the file, which is internetspeed.xlsx. I just did a method called describe on this data frame, and it kind of shows me all the descriptive stats. So the sample sizes, the means, and the standard deviations, pretty much the same as you saw earlier. And in order to perform a t-test with two samples, you have to mention the samples. So I'm writing the sample 1 and sample 2, and I'm to mention what kind of alternate hypothesis we want to do. So we want to do a two-sided test in this particular case. So in Python, if the sample sizes are not equal, then you have to mention that for any value which is nan or not a number, that is to be just ignored. So it doesn't really worry too much about the samples not being equal after you explicitly mention this. And if you can see, the calculation of the test statistic here is -6.87. If you remember, this is exactly what we got in Excel as well. And what is the p-value we got in Excel? Let's just get it from here, 7.58 multiplied by 10 to the power -8. You can see that's the same p-value that you got here. Again, as I said, these methods are smart enough so you don't have to do any adjustments to the p-value. Once you've mentioned it is a two-sided test, you have to simply compare this p-value with your alpha, which was 5%. So once again, the p-value is much less than alpha here, and we can reject the null hypothesis. Also, please note, if you're performing this test, but the variances are not equal, or that assumption is not satisfied, then I can show you within this function, there is a parameter where you can change this value. So let me just do a shift tab here, and it opens up a window. I can maximize it. It says equal variance has been set to true. It's doing the calculations, assuming the variances as equal. It's using the pooled standard deviation, which is the first option. But if you say that the variances are not equal, or let's say you do a test and find out that the variances are not equal, in that case, you may put this to false, and it will then perform the Welch test. Like I said, I'll be talking about the tests on equality of variances a little later. Right now, we are in the middle of comparing the means. So we just want to get done with that, and then we'll start the next sequence. So that was it about the two-sample t-test with independent samples. Next, we'll be talking about the two-sample t-test with paired samples. Thank you.